concern I have is you've got 75 minutes during the class period. The problem that you're going to have is mostly time. So it's not the equations. The equations you're going to have in the cheat sheet. So if you want to, I mean, we can discuss it openly right now. I think it's more efficient if you have one page. That's the reason why I actually have one page rather than a card-based system where you run back. I just wanted one page so everybody could just have their equations in front of them and not spend the time looking around, flipping through it, and doing that. I'd rather you spend the time on solving the problem itself. So with 75 minutes, there's just not enough time. So we're going to try to stretch it right before the class after us, but I would recommend that we stick to the single page just because of the inefficiencies of flipping back and forth.
I think you log out really good at I think you log out really good at
I think it's going to take quite a bit of your time. Is that, everybody's in agreement with that? Yeah. You're not going to complain about time? Can't hear. All right. Well, no, don't complain about time. So, I'm trying to make it as efficient as possible by having a single page. Here's the thing. So, single page, front and back. So, people that do want to be efficient, I recommend do it on one single page, front page. But it's up to you if you want to use the dual page. You're going to put all the equations you want in that single page front, or if I give you two sides anyway. Now, there is a catch, obviously. You are going to be turning these with your exam. So I want to see what you're actually putting on the paper. Doesn't affect you at all in terms of grading-wise, but just for me as an FYI, what are the general consensus? Are people just writing example problems, or they're writing the equations that they need? So that's all. But it's up to you how you want it. So we can have it front and back, so I have no problem with that. The only issue is if you want to be efficient, I would highly recommend there's 75 minutes. Most likely it's going to be 3 problems. So you're just going to have to be efficient with your timing. That's the main concern. Question?
We have notes in our equation sheet.
Notes? What do you mean by notes?
Like example problem, percentages.
You can have whatever you want in it. So I don't mind what's in there. I'm going to take a look at it. But that's mostly information for me to see, what are you putting in there. Right? I'm hoping that these are primarily based on understanding more than anything. So it's not here after your break. I'm here after teaching you. So if you had done the semester don't learn propulsion, then I failed in trying to teach you. Right? So the grade doesn't matter to me as much. So it's important that you understand the equations and apply them correctly to some of these problems. And they're mostly based off the homework problems. So if you know how to do the homework problems, you're going to know how to do the exam problems. But definitely study material. Example problems we're doing in the lecture as well. So nothing is outside of the lecture or the homework notes and problem solutions and things like that. Any questions on that? Good? Okay, homework number 3 will be posted today, and it will be due a week from today at the beginning of class as well. And it will be also the same principle that we're doing right now, similar example problems, and this is actually a more extensive problem, but very, very similar to this. You're just applying it to different fields and whatnot. Okay, so last time we started doing example problem when we had methane and air reacting at 400 Kelvin. We had a force ratio of 0.8, which was a lean fuel condition, and we wanted to find the heat of combustion or the lower heating value or the heat of reaction. And I will show you later on why are we interested in those. I mean, what are these properties? Why are they important for me from the propulsion standpoint? We're going to see that today, actually. But we're doing all this for the adiabatic flame temperature, which we're going to get. But anyway, so I already know the equivalence ratio is 0.8. Now, from the previous example that we did in a lecture, because we had a slight follow-up on this after class last time, where did I get this chemical balanced equation? If you looked at the lecture notes from the week before, we had an example in the lecture note where we had this chemical balance equation, we had these coefficients, and we went and evaluated these coefficients, and A turned out to be 9.52. So these are the same coefficient, same chemical balance equation. Now, I got this for a stoichiometric condition, meaning ideal fuel-air concentration that I have, all the fuel that I'm putting in, all the oxygen that I'm putting in to this mixture, I'm burning and I'm converting into three main species that come out, or compositions that come out: water, CO2, and nitrogen. Nitrogen just floats around. Actually ends up being, nitrogen is your working gas because the majority of your mixture is nitrogen. Or the majority of air is nitrogen. So this is my equivalence ratio in terms of stoichiometric condition. Now I want to find out what is my fuel-air ratio for this lean condition. Well, it's simply of that ratio here, which is fuel-air ratio of the condition of interest relative to the stoichiometric fuel-air ratio. So based on this, you just do the cross multiplication, and what you get is a fuel-air ratio that makes sense that it's smaller than my stoichiometric condition. So if you ever in the exam and you do the cross multiplication incorrectly, and you realize you're getting a higher fuel-air ratio than you did with the stoichiometric condition, then you know for a fact that you did something wrong in the cross multiplication. Question?
So would the stoichiometric fuel ratio be the ideal condition?
Yes.
Okay.
Yes.
Is that a given value, or do we solve for that somehow?
No, you're going to be solving for it, buddy.
How do we do this?
Revisit the example from last class, last week's class, right?
Guys
Right
believe in
here.
ghost stories, buddy.
Right here. Did you do homework number 2? Okay, you have to do it as well.
I did that part wrong, which I didn't do until that day.
I love this guy.
Well, yes, you.
Me and him is gonna be
Unless
best
I give
friends.
it to you the problem, but most likely you're
Yeah,
going to
your
have
type.
to actually determine that, because you do need to know what is your stoichiometric balance ratio that you're putting into that engine, no matter what. So whatever fuel I give you to use in an engine, JP8, JP5 fuel, whatever fuel that you're going to use, you actually have to figure out that stoichiometric value, because you're most likely not running at that stoichiometric value. That's your reference base. So ideal fuel and air mixture conditions. Anyway, so from that we went and got our mass of fuel based on assuming that I have 1 kilomole of fuel and using our molar mass. And then from there, knowing my fuel-air ratio, I got my mass of air. And from my mass of air, using the molar mass of air, I was able to get the number of moles for air. Now, do keep in mind the molar mass of air. That's something that you want to have on your cheat sheet in general. I don't know. Sometimes I assume that these things are going to be well known. But for example, CH4. What is the molar mass for CH4? 16. How do we know 16?
Carbon. Yeah.
What is it?
12.
Carbon is how much for it?
12.
12. And hydrogen is, in this case, 4. And each one is 1. So if I give you whatever fuel I give you, you should be able to compute that, right? Okay. So from there, we outlined our chemical reaction for this mixture, where we had a 11.96, which we got from the number of moles, or the amount of moles that we have for air. So knowing that I had this much air, I put this in my chemical balance equation with 1 kilomole of fuel. Then I got excess nitrogen and oxygen. Why? Because I'm running lean. So if I'm running lean, I'm not burning all my air that I'm putting in that mixture. I have less fuel than I have air, or oxidizer in this case. So most likely, given the fact that I'm running lean, I'm gonna get excess oxygen and my nitrogen, it's gonna be different than the total amount that I'm putting in here compared to my stoichiometric condition, meaning it's not going to be 9.52 multiplied by 0.79. No, it's 11.96 multiplied by 0.79. Now, if I'm running rich conditions, fuel-rich conditions, what will happen? How will this chemical balance equation change?
Here? No, fuel.
I'll
Excess
have
fuel, excess fuel.
extra carbon and hydrogen. So I have CH4, I have oxygen, I have nitrogen, right? This is excess, so I didn't burn all of it, and I ended up with primarily extra oxygen.
Yeah,
Okay.
hydrogen.
So if I'm saying that, okay, it's rich, meaning the fuel is
Fuel.
higher,
So it's hydrogen.
so what do I end up with here actually? CH4, yes, nothing. I end up with excess fuel. That's why you're not burning efficiently. And that's how actually most systems are running. But you're not burning all your fuel. You end up with CH4 here. If you're running rich, and we get this
Excess fuel.
4 as well.
Yeah.
Please look at your notes.
You don't know.
It's in your notes. You'll get CH4 excess here as well. Okay, so from there we got the Q per number of moles that I have, equation that I had, and we outlined the heat of formation for the elemental species that I have there. And we said, well, the heat of formation for oxygen or nitrogen or any of these elemental species, there is no heat of formation for them. They're already existing in nature, so they're zero, so they cancel out. All I have to worry about is the composition-based species. These are the ones that I need to account for. And then from there, I needed to evaluate my CP values. So these I could get easily. Now, the issue that I'm having is finding my CPs. Now, to find my CPs, we said, well, it's equal to the summation of my mole fraction multiplied by the species CP itself. So we needed to get our mole fractions. And we went and got my mole fraction for water, in this case. Water is on the reactant side of things. So after the lecture last time, people asked me, it's like, okay, what is 2 plus 1 plus 9.45 plus 0.51? Where are we getting this information from?
Number of moles.
Coefficients.
Of what?
Products.
Products. Right here, these coefficients. 2, number of moles, 1, CO2, 9.45 is for nitrogen, and 0.51 for oxygen. So the same thing, if I have this as products, so if I have this as products, and I'm trying to figure out how much of H2O do I have in this whole amount, then how much is it? 2 divided by the total sum of coefficients. So 2 divided by 2 plus 1 plus 9.45 plus 0.51, which is what you have right here. Now you just did this for homework number 2, right? Same thing for CO2. CO2, same thing, 1 divided by the total sum. And nitrogen, well, nitrogen is 9.45 divided by total sum. And oxygen is 0.51 divided by the total sum. So here, actually, you might want to, if you're solving this and you're trying to be efficient in timing, you just want to get the total and just questions thus far? All right, so this is where we stopped last time. Now I need to take these and find out my CP for products. So what I ended up doing is getting the individual CPs for each of my species that I have to do with, which is CPI. So CP of H2O is equal to 41.3 kilojoules per kilomoles Kelvin. And CP for CO2, 54.4 kilojoules per kilomoles Kelvin. And CP of nitrogen is equal to 32.8 kilojoules per kilomole. And then CP of oxygen is equal to 34.9 kilojoules per kilomoles Kelvin. So from all this, what do I get? I'm going to get my CP, knowing my mole fractions, knowing these CPs, multiply them together, and I can get my CP of products is equal to 35.82 kilojoules per kilomole Kelvin. So now I need to do the same thing for reactants. So CP of reactants is equal to the summation of the mixture fraction, or the mole fraction, sorry, of, and multiplied by the elemental species specific heat or constant pressure. So the mole fraction for CH4 is equal to, so what is that equal to? So I have this equation up here for you. What is that equal to? What is next to this?
1 over
1 divided by? Well, I'm going to write 1 plus 11.96 so you have it in your notes. Okay? But yes, you're correct. Which is going to be 0.077. The mole fraction for oxygen, obviously the total is going to be the same. 1 plus 11.96. And same thing with nitrogen. 1 plus
shouldn't it be 11.96 times the 0.21?
So oxygen, how much is that?
The denominator never changes, it's the total.
Correct. So 11.96 multiplied by 0.21.
Yeah.
And same thing with nitrogen, 11.96 multiplied by 0.79. So
Yeah, you're right.
yeah.
Yeah.
For you and 0.729
Did you do homework?
and 1.94.
I did not.
Now, I already have CPs for oxygen. I already have CPs for nitrogen. So all I need is CP for methane. So the CP for methane is equal to 36.1 kilojoules per kilomole Kelvin. From there, I could get my CP of reactants, and my CP of reactants is equal to 33.46 kilojoules per kilomole Kelvin. So, now that I got these CPs, I need to get back to the equation that we were trying to solve, which is right here. I need heat of formation. Heat of formation is equal to Q over the number of moles of fuel. So I need my heat of formation of water, CO2, CH4, but given that these are known values, we're going to actually list them up. So if I'm giving you a problem, I'm going to be providing you those, or tell you to look it up in a table in the book. but for CH4, it's 74, 873 kilojoules per kilogram.